Parallel Gaussian channel I want to talk. So goal of this lecture is to determine the capacity of parallel Gaussian channels. And basically it will lead to how to do power allocation across the parallel channels. So here are the motivational questions. So we learned that if the signal power is given to be P, and the capacity of a Gaussian channel with the noise power N, so we have a SNR, which is P over N. P over N is SNR, and that is well understood. Basically, the capacity is half times log 2, 1 plus SNR. Given this, what is the channel capacity if we have multiple Gaussian noise channels? So in such a case, how you are going to allocate the power, okay? And what is the capacity in that case? So in order to talk about multiple channels, we can start thinking about the capacity for two parallel channels. So there are two independent Gaussian channels available to a channel. Let's suppose the first channel introduces white Gaussian noise with the power N1, so noise power N1 is equal to 7. The second channel does that with N2 equals 1. So one channel is very noisy, the other channel is less noisy. And these two channel noises are independent with each other. So that is the setting of this question. In such a case, what is the channel capacity? How you allocate the power? That's the problem. So what is the capacity of this channel? So in order to answer the capacity, we need to know P, the power constraint. So that should be the answer. And if you know the power constraint, then we can begin to talk about this type of capacity, right? So let's do an example. Let's suppose that P is equal to 3 when the noise power is 7 in one channel, let's say first channel, and the noise power is 1 in the second channel. So using your insight, which one would you like to use more in this case? Noisy channel or less noisy channel? Obviously, you would like to use less noisy channel first rather than very noisy channel. That could be your intuition. Okay, so let's try to check your intuition. Okay, so what is the capacity of this channel? All right, so using your intuition, the intuition tells you I need to use less noisy channel more. Okay, so let me open up the pen. So your intuition says use, oops, what is happening? Your intuition tells you use less noisy channel. More, right? Probably that is your intuition, and let's check your intuition. So in this particular case, this one is less noisy channel. The second channel is less noisy than the first channel. Okay, so let's think about allocating all the power to the second channel. What is the capacity then? So you are using, let's say, first channel, second channel, right? You are allocating, let's say, power, let's say P1 is 0, P2 is 3 in this particular case. Then in this case, you will achieve nothing. You will have no information sent over the first channel. So first channel capacity is 0. And for the second channel, the capacity is going to be f log 2 1 plus 3 over 1, right? So because N2 is equal to 1. So in this particular case, the capacity is the sum of the two, which is this one, the half log 2 of 4. So it is log 2 of 4. So it is 2. Log 2 of 4 is 2. 2 times half is 1. Okay, so the capacity in this case is equal to 1 in this power allocation. What happens if you allocate, let's say, all the power to noisy channel? Let's say P1 is equal to 3 and P2 is equal to 0. In this case, the second channel, you have no rate transmission there, and for the first channel, you have f log 2 1 plus 3 over 7. So in this case, this one is much smaller than this capacity right here, right? It was log 2 of 4. Now it is log 2 of somewhere around log 2 of 1.4 only, right? So what's inside the log determines the inequality, which one is greater. So in this case, you can immediately see that this type of power allocation using more noisy channel, allocating more power to the more noisy channel is not good. Okay, so your intuition is right. But here, this is just the checking the intuition, but I'm not sure, we are not sure if this is the optimal solution, right, or not. So that's the problem that we need to talk. And this simple calculation tells you in this case where P is equal to 3, you get this power. You get this capacity. Capacity is like this, and you might want to say, can I increase in this particular case? Let's say first case. Let's say case number 1. Case number 2. In case number 1, am I going to get any better capacity if I allocate non-zero power to the first channel? So we let's say take away a little bit and give it to the first channel, right? Would this make the overall capacity, the sum of the two capacities, greater? So if I allocate non-zero power to the first channel, would it make it better in terms of the sum capacity, sum of the two capacity, sum of the and the sum capacity? What I mean by that is capacity of first channel and the capacity of second channel, and add them up. That's the sum capacity or the total capacity. Well, in just the capacity, okay, without the channel index. So that's capacity without the channel index means sum of the two capacities. Okay, in such a case, if I take away a little bit and give it to the first channel, would it make it better in terms of capacity? You don't think so, right? So in this particular case, we think that case one is the optimal solution. We don't want to give any power to the first channel in this particular case. And but it depends, right? It depends on the power budget that we have. So if we increase P to 7 in this particular case, we can investigate further, okay? So in this particular case, when P is equal to 7, we can talk, right? So let's consider when P is equal to 7, what happens, okay? So we can continue this evaluation, right? Evaluation, we continue. And this one, P is now equal to 7. P is now equal to 7 case. And here I give all the power again. So to the second channel. So P2 is 7 and the P1 is 0. In this case, what is the capacity? In this case, that is log 2 of, let's just forget about half for a while, because that is not the determining factor. Half is not the determining factor, which one is greater, okay? So that is 1 plus 7. So in this case, it is 3, okay? Well, 3 over 2 in terms of capacity, right? So that is the case, but would this be the optimal, the best solution? So let's try different one. So let's say P2 is, let's say 6, okay? We allocate 6 units of power to the better channel, and let's say use 1 unit of power for the first channel. So in this case, I will achieve log 2 of 1 plus 1 over 7, all right? And this one, I will achieve log 2 of 1 plus 7 here, okay? And then if we add them up, if we add the two capacities to get the capacity, what do we get? So adding the two, log 2, 1 plus 1 over 7, plus log 2, 1 plus 7. That's what we are doing to get the capacity. So this one is what? Log 2 of 8 over 7, okay, and this is log 2 of 8. So the sum capacity, sum of the two is log 2 of 8 times 8, 64 over 7. So what is 64 over 7? 64 over 7, 64 over 7. Okay, so we divide by this, so it will be 7 times 9 is 63, and so it is about 7.1, okay, 9.1. So that is equal to, I mean, in the ballpark, it is log 2 of 9.1. Okay, so in this case, which one is bigger? So the capacity solution, let's say case 1, allocating all the power to the better channel, and compare that with the case 2, where you have some power given to the noisy channel. And this one says, which one is bigger? Obviously, this channel, I mean, this power allocation achieves a better capacity. So this intuition is making sense, but it depends on what power level is given as a power budget. In this particular case, we could achieve better capacity by giving some power to the noisy channel as well. So how do we determine the capacity in general? How do we optimize it? Okay, and then we can continue further with other greater power budget, but the critical question is this. Okay, the critical question is, how do we optimize the power allocation so that the capacity of the parallel channels can be obtained, okay? Because the capacity is the maximum that is achievable, okay? So that is the motivation for parallel Gaussian channel capacity. And another motivation is that if we allocate power to a certain channel, we get diminishing return. Basically, it's the argument is inside the log, and that's what you get as the return value of a power allocation. So if we consider this log function as you, well, so here is a power allocation, right? So this is log 2 of, in this particular case, is 1 plus x over 7 versus log 2 of 1 plus x. So let's say this is that curve, and the other curve that we have is this curve. So it goes slower, right? Slowly increase. So this is that curve, and this is that curve. So in the small power budget case, you would probably use the better channel more, but as you continue on, you notice that this slope is flattened out. So you for a unit of for a unit value invested, you get diminishing return. So in such a case, then probably you would better to use your unit power for a noisy channel so that you get better return. So we need to compare the slope of these curves, two curves, in order to allocate power. And then the best way to deal with such problem is to use calculus, okay? So use a Lagrange multiplier. We allocate, we find the best allocation to get the optimal return. So that's what we are going to do. All right, so let's move on with so we have completed the motivational questions and a little bit of back of the envelope calculations to test our intuition. The intuition tells us that use the less noisy channel more until you get good return for your unit investment. And then at a certain point, beyond a certain point, you better use the noisy channel as well, right? Because the better channel has reached diminishing return, so that you are move into the area where your return value is smaller than the return value of the noisy channel. Then you will allocate some power to the noisy channel as well. So that's the intuition that we have developed in the motivational page. So here is the setting for parallel Gaussian channels. So we have a multiple Gaussian channels where the noise added to the signal is Gaussian distributed with a power level. So Z1 with variance N1, Z2 with N2, and so on down to Zn. Okay, and the power constraint that given is expected value of the sum of the powers that you allocate to the input signals should be less than or equal to P. Okay, and the capacity is maximum of mutual information between X and Y, the vector X and vector Y. Okay, so this channel can be written as X plus Z equals Y, where Z is Gaussian distributed with a zero mean and variance of this. So variance here is the covariance matrix, right? And here in this particular case, I will talk about the noises are uncorrelated with each other. So this here is diagonal matrix. In general, we can deal with a non-diagonal matrix case where KZ is not diagonal in general. I will do this, uncorrelated case first, and then I will deal with this correlated case next. Okay, so in this particular case, all we have to define is this covariance matrix of the noise, and given this channel, we want to find the capacity of this channel. So the capacity with a constraint on the power. Okay, so we have this much power given to you. How you allocate this power to different channel so that you can obtain the capacity. So that's the parallel Gaussian channels. And firstly, I will talk about Iid Gaussian with the fixed variances. or equivalently, so this one is here, parallel Gaussian channel, we can talk about this type of channel where WK is Iid Gaussian with a fixed variance. So fixed variance means, let's say, sigma I is all equal to, let's say, n. So same fixed power for all I. So that's what I mean by this. And it is Iid. So when we talk about Kz, this Kz has a diagonal matrix where non-diagonal elements are all zero. Diagonal elements are all equal with the n. And the Hk is the multiplicative factor to the transmitted signal. So we can talk about the multiplicative factor as well. So if this one is a large number, then we have a high signal to noise ratio. When this Hk is small, then we have low signal to noise ratio. So in such a channel with a multiplicative factor can be equivalently described as this channel where the noise Zk is independent Gaussian with a different variance. So in this case, we can scale up or down based on this Hk so that we can have Kz in this case, N1, N2, and small n with a diagonal because they are independent. So depending on this number, right, the variance can be described by the signal to noise ratio. So for example, if this was 1 right here, then the signal to noise ratio, let's say for two channels, let's say H1 is equal to 2, H2 was equal to 1. Okay, suppose, right? Then in the first case, the SNR is 4 over 1. The second case is 1 square is 1, so 1 over 1. So SNR is 4 over, 4 and 1 in this case. And in this case, then we can equivalently say that by dividing the first equation with 2, so the first equation with 2, right? And so we are normalizing the signal power to be 1, then the noise power can be described as 1 over 4, and this one with N2 equal to 1. Okay, in such a case, we can talk about the the expected value of xk squared is 1, so the signal power is 1, and with the noise power for the first channel to be 1 over 4 and the second channel to be 1, then we have an equivalency between this channel and this channel. Okay, so that's the variation of parallel Gaussian channel problems. So you can talk about the multiplicative signal channel case as well. Okay, that's this part. Right, now let's move on with capacity. So capacity is the mutual information between X and Y, subject to the power constraint. power constraint is the expected value of the random variable, sum of the random variable, xk square, that should be less than or equal to p. And mutual information, by definition, is entropy of y minus entropy of z. But z here are assumed to be independent with each other. In this case, that was the assumption, right? That noisy correlation covariance matrix is diagonal, so that we get this. So this can be upper bounded by sum of entropy of yk. Okay, so that is the independent assumption, that y are independent. The elements of y are independent with each other. That can be achieved, right, with the covariance matrix of, that can be achieved, right? So the equality can be achieved when y is Gaussian, okay, with each element independent with each other, okay. And for each k, we have Gaussian y and Gaussian z. So that capacity has been calculated, which is half times log 1 plus SNR for each channel, okay? So the mutual information is upper bounded by this quantity right here. And basically, the last case is obtained when you choose y to be Gaussian, okay? So y to be Gaussian, okay? And then the equality is achieved when y is Gaussian. Y is Gaussian, and that case is obtained when x is Gaussian, okay? When x is Gaussian with the covariance matrix, let's say kx is a covariance matrix of x, and if it is a diagonal like that, then these two equalities for 1 and 2 are met. Okay, so that's going to be the capacity formula for Gaussian channels when the channel noises are independent with each other case. All right, so that's the capacity formula. So it is the sum of logs, right? That's the formula. And then in this, that is still a formula, but we need to find the distribution of x, right, with the power constraint. We have identified the distribution has to be Gaussian with the covariance matrix kx. That has to be diagonal, so that xi's are independent with each other. So xi's are independent Gaussians with the power allocation P1, P2, Pn. So having come to this conclusion, there's a small result right here. What we have to now, what we have to do further is identify. So in order to find the capacity, we need to optimize the right-hand side of equation 2. So we need to optimize this. So we need to optimize this by finding the power location vector. Let's say this vector. We have to find this vector to find the capacity. Okay, so in order to complete the maximization, we need to find the best power allocation vector P, so that we get optimized right-hand side of equation. I mean inequality 2. Okay, in this this number has to be maximized with the given power budget P. So here the power budget is nothing but sum of these numbers is equal to P. Okay. So with this constraint, we need to find the best allocation vector P, so that right-hand side of inequality 2 is optimized. So that is the problem. So here I summarize it again. Now we need to find the optimal power allocation vector P. Okay, so P is the variable for in calculus. Okay, so consider the Lagrange multiplier, which this is the objective function. We need to optimize this number. I mean this formula. I mean this function. So find the maximum of this function given the power constraint. So we give power constraint right here. And the lambda is the Lagrange multiplier. So that's the objective function now, with the constraint that these pKs, since they are power allocation, that cannot be negative. So it has to be non-negative for all k. And then sum of these pKs should be equal to P. So these this is the problem we now have to solve. Okay. All right. So in order to do that, basically we need to take the differentiation with respect to pk. So pk's are unknowns. I mean the pk's are the optimization variable. Okay, so we need to take the derivative with respect to pk. Okay, and then so since you have log, when you take the derivative, it is inverse of the argument. So we get this, and then for for each pk, we have a lambda. So we have this. So we set this equal to 0, then basically P plus nk should be equal to 1 over 2 lambda. That's the small conclusion, right? And hold on a sec. That's the small conclusion right here. And then we are going to let, so that's the result that we get from the first, this line. So from this line, we get this. And then we are going to let L is defined to be 1 over 2 lambda. L is defined to be 1 over 2 lambda. So, we have pk plus nk is L, and then pk is L minus nk for all k. So we find the pk once we find L. Once we find L, we can find the pk. And then in order to find the L, we need to apply the power constraint, which is non-negative. and the sum of the pKs should be equal to P. That's the only step that we need to apply. So let's do one by one. In this line, I applied that the power, so each pK is non-negative. So I'll use L minus NK argument plus. So that means this is the argument plus is equal to, let's say, the argument itself when argument is greater than or equal to 0, right? When argument is less than 0, it is 0. So that's the operation, argument plus. So pk is L minus nk, and when L minus nk is non-negative, pk is equal to L minus nk. When L is smaller than nk, it is 0. So that's the first one. And once you have that one, and I think I have it here, then the water filling solution says the solution pK is this, L is chosen such that sum of these powers should be equal to P. So this is called the water filling solution. You will see why it is. Okay, I'll give you an example. So in this case, the condition pK is non-negative makes the problem difficult, right? But this here is the solution. Once you apply this solution, then you can obtain the capacity. Let me see if I have that expression. So once you apply that capacity, power allocation. So for each pK, we apply that power allocation, right? And using the plus sign one more time, this becomes water level L over NK, and the log of L over NK. And this plus sign is again the same. When the argument is non-negative, it is log L over NK. And when it is negative, it is equal to 0. Okay. So just by substituting that power allocation that we have done, where we have pK was in previous page, it was what? L minus NK plus, right? So when this you apply this, then basically log 2 1 plus pK, which is L minus NK over NK, right? And we are applying this one plus, right? So when this is non-negative, then it is log 2 of, so you cancel, one is cancelled with the NK over NK, so it is L over NK, right? But when this one is negative, then basically we don't have allocation, power allocation. So this is 0. So log 2 of 1 is 0. So all we had to do is to add this positive sign at the superscript. Okay, so that's the, so it is either this or 0. Okay, it is either this or 0. Okay, so this happens when any L is greater than NK, right, or equal to. Okay, 0 happens with this case. So that is the water filling solution. Okay, so given a noise level like that for multiple channels, and we find the water level L. And when the channel is too noisy, like this one, we don't allocate power there. And when we have water level to be greater than the noise level, we allocate this much power. So that's PK, right, for each channel. And here is noise channel, power of the noise channel, NK. So that's the solution. And some of these areas, so these areas, some of these areas is supposed to be the power constraint. So some of these power location, okay, so this area should be equal to P. So the problem is now find the water level L for a given power budget P. Once you find it, since these channel variance, noise variance, N1, N2, all the way up to Nn, since they are given to you, you can find power allocation for each channel. So the problem comes down to find the water level L that satisfies the power constraint. Okay, so that's the problem. So how to find the water level L? I have given a M5 for MATLAB, which determines the water level, given two inputs, a vector of noise levels, VEC. So VEC is basically that this noise level vector, let's say that we call vector M, right? So given this and the total power constraint P, this is the total power constraint P. So in this case, we need to iteratively find the water level. So this noise level is given to you, power budget is given to you, and the tolerance is some small number for convergence, right? If the tolerance, the difference of the approximation comes within tolerance, you stop, okay? So basically, in this particular case, you find the water level by filling up the water, by pouring the water to the noise, flow, like that. So if noise flow is like that, if you pour water, when the water, total amount of water is small, you are only utilizing the best channel. So these are the noise levels, for example, N4, N5, N6, 6 channels. Right? As you have more power available to you, you increase the water level, so the total power location increases. But as you increase your water level, you are including other channels for usage and as well. And so if your water level rises, the total power budget increases, or the other way, if your power budget increases, water level increases. And as you continue to increase the water, the total power level, the water level continue to increase. And in this particular power level, the power budget, basically you are utilizing all 6 channels, right? But when you compare with the initial one, where your P is very small, you are using only the best channel. Okay. So in order to find this water level recursively, you are um, you are just implementing this uh, intuition that we have developed right here in this picture. So given water level, given power budget, you are allocating the power to the best channel, and then if you have still more power to be allocated, you divide it by the all you divide the power, leftover power, to other channels equally, and then you find out the uh, some power again, and you continue to increase um, as you as you do the iteration. So basically, maybe we just need to take a look at this algorithm here. So given this two inputs, right? First, water line is determined to be this. Let's say the minimum of the vector. In this case, n3 is the smallest, so this is equal to n3, and water line is basically n3 plus some power, and then you divide the power, total power, equally to all 6 channels. So that is the initial water line. So obviously that is not good, but it is okay to begin with. Okay, so the P total in this particular case, now you are looking, that is your water level. Water line is L, so this one is L, and the L minus NK, you do this, that is your PK, and you need to do the summation of all of them, and that has to be, right, equal to or less than P, right? So you do that, and then if this sum of PK is smaller than total power available P, then you take the difference of the two and then do more allocation equally until you have these sum of PK and take away the P that is smaller than epsilon, the tolerance level. Okay. So you continue to increase the water level L until you have this convergence. Okay, that's what this algorithm does. And here is an example. Let's say 7, 10, 3. You have 3 channels with these noise powers. And then total available power is 12. Tolerance is 0.1. And then it will return immediately this value. So basically, in this case, you have first channel noise level is 7, second channel 10, third channel 3. And the power allocation P1 is L minus 7, P2 is L minus 10, and so on. So you need to find L, but this one answer is water level is this, okay? And in this particular case, then sum of the 3 power should be equal to 12, okay? That's the power constraint, okay? All right, so that's the solution for capacity. Once you find this solution, all you have to do is substitute this into that formula that we had, and F log 2 1 plus pk over nk. You substitute into this formula, then you will get C. And this is the capacity because it has been maximized. And how do you achieve this how do you achieve this capacity? And then we go back to that picture that we started with. The problem we had started with was x plus z is equal to y, where z is Gaussian distributed with kz, where kz look like 7, 10, 3 zeros otherwise. So that was the problem. And then the solution says x need to be Gaussian distributed with the mean 0, and kx, the covariance matrix of x, should be 3.6667, 0.6667, 7.6667, and rest of them are all zero. So that should be your solution. So use this random vector x, which is Gaussian distributed, whose mean is 0, covariance matrix look like this. Then you will achieve the maximum capacity over this channel. So that's the complete solution. Okay, I will talk about colored, Gaussian, parallel Gaussian channel capacity for colored case, where kz is non-diagonal in general.